Hello, everyone. It is the Prophet Michael David, aka Aries, and I hope everyone is having a great day. I was going to make this video a couple days ago. I mean, my channel isn't that popular, but like one of my more popular videos was the twin prime conjecture solution. So this is the follow-up video, but I'm doing this because I found other ways to describe it, and I'm always at God's behest to dumb this down as much as possible to make it easier for you all to understand. No offense. In other words, I am always at the behest of God to recognize this quote, which I've seen before from one of the greatest mathematicians ever, David Hilbert. So, as I am a fan of Rick and Morty, as a lot of you are, here goes a twin prime solution video number 2. Here we go. Here we go. All right, quick refresher for that screenshot. The purple numbers are just squares of primes. You can ignore those for right now. The blue numbers and the green numbers are my x numbers, which are modified prime squares, which conform to this equation. Again, those are my x numbers. Now, if you want to convert an x number back into a prime, you use this equation. Now, here's the important part. Those x numbers already exist on the times tables and they form two lines. It's just a pattern that I picked up. But if you want to convert the entire times tables to primes and other numbers that are on the 5 mod 6 and 7 mod 6 lines, all you have to do is put that equation into the times tables and you will get out a graph like this. So, in other words, to make that graph or that version of the times table, all I did was assume everything on the times table was x numbers, then converted it into primes. And if it did not come out as a whole number, then it just became a zero. I just use a filter, an if statement. And that's how you do it. Everything that will be left will be either a prime or a composite prime or of a square of a prime that's located on the 5 mod 6 line or the 7 mod 6 line. And as you can see, the timetables themselves, it's symmetric. You can, if you look real closely, you can see all the numbers make like it's like an increasing wave. Brings us to infinities, which is an awkward conversation, but one we got to have. We've talked about it a little bit before, but look at the times tables. So the times tables are kind of a hybrid of infinity for this reason. All right, as we've discussed in a previous video, I think it was actually one of my first, there are two kinds of infinity. And in this video, I'm going to introduce a third. But the two basic kinds of infinity are number one, a regular infinity, sometimes known as a countable infinity. And then the second is a transcendental infinity, aka an uncountable infinity. All right, firstly, the regular infinity, countable infinity. That's like the game we used to play when we were little. You know, who can count higher? Infinity, infinity plus one, infinity plus two. The basics of a countable infinity are that you have two different sets of numbers. It doesn't really matter what they are, but you can always draw lines from one set to the next set and they all match up. So you can have two sets. You can draw a line from 1 to 1, 2 to 2, 3 to 3, 3 to 4, 5 to 5, 6 to 6. Or you could have two sets where you had one drawn to infinity plus one, two to infinity plus two, three to infinity plus three. Or you could have another one where you have one to infinity, 2 to infinity plus infinity, 3 to infinity plus infinity. All of these are still examples of normal infinities, no matter how abstract or big you think they are getting. It's just that you can always draw lines from one set to the other, and that is a distinct feature of normal, aka countable infinities, and those are the infinities that everybody loves, especially geometers. And secondly, we have transcendental infinities or uncountable infinities. And those are, it's basically, to put in layman's terms, they're the majority numbers in the universe. They are like the quicksand. To put it metaphorically, there are infinitely more numbers in between 0 and 1 than there are from whole numbers from 1 to infinity. I know it sounds stupid, but they are literally, there's no, you cannot match them up with lines. There's no algebraic equation that you can come up with to actually calculate them. They are just random numbers with random numbers. That's what they are. And they just go down. It's like quicksand forever and ever and ever. Like between 0 and 1, there's always a number in between that. Between 0 and a half, there's always a number in between that. And it just goes down. They're like fractals. So how does this pertain to the primes and the times tables and my x numbers? Well, let's look at the timetables with my x numbers on it one more time. Now, if you're still thinking of infinities, which you probably should be, across the top, the x-axis is 1 to infinity. The y-axis is 1 to infinity. Those are both normal infinities. But the x equals y, the squares, also 1, 4, 9, is also a normal infinity. The trick here is to think about the times tables in their reciprocals and reciprocal sum. In that way, I mean, instead of thinking the top 1, 2, 3, 4, 5, 6, 7, 8, infinity, y, think of everything as a summation of 1 over that number. So across the top, you would add 1 plus 1 plus 1 plus 2 plus 1 plus 3 plus 1 plus 4. Y-axis, you would do the same thing. 1 plus 1 plus 1 plus 2 plus 1 plus 3. That is what's known as the harmonic series, and it's well known that the sum of the harmonic series goes to infinity. It's kind of like a card or a deck of cards where you lay one card on another, and each card becomes thinner and thinner and thinner and thinner. But since you have an infinite amount of them, the height of the deck of the cards is still infinity. Now think of doing the same thing to that 45-degree line, x equals y, the reciprocal sum of the squares. So 1 plus 1 plus 1 over 2 squared, which is 4, plus 1 over 3 squared, which is 9, plus 1 over 4 squared, which is 16. That summation, which is known as the Basel problem, which was solved by Leonhard Euler, is approximately 1.6 something. It's pretty close to the golden ratio. So why did I go through this long-winded speech again about infinities? It's because it's important. The main point being that line segments and lines don't really convey much information, and if you try to sum them up, you're always doomed to get infinity as the answer. Whereas if you try to sum up shapes, triangles, squares, rectangles, and you have all shapes, you can do it and get a definitive answer. And that's how my twin prime solution, I'm going to describe it to you now. All right, if you want to find all the prime numbers as quickly and efficiently as possible, you do it the following way. One more time. The blue numbers are 5 mod 6 primes that are in X number form. The green numbers are 7 mod 6 primes, which are in X number form. And those pink numbers, that's the line that runs right between them. And that line is the 6 n squared line. N equals 1, 1 plus 6 is 6. N equals 2, 2 squared is 4, times 6 is 24, 3 is 54, etc. And if you watched my last video on the primes, I explained why all prime squares had to end in 1 or 9. And for that exact same reason, all my x numbers end in 0 or 8. So if it ends in 8, then it has to be a prime squared that ends in 9. And if my x number ends in 0, it has to be a prime squared number that ends in 1. And by that, I mean it can. I thought about erasing that last video and rephrasing it, but this is a better teaching opportunity. If the x number ends in 0, then it can possibly be a prime squared. If it's not, it's a composite number. Or if it ends in 8, it has to, or it can be a prime number that ends with 9, or it can be a composite. It's possible. Those are the only numbers that are possible to be prime. It's non-zero that they are prime. So then to solve the twin prime conjecture, you just do this. Since any number on those lines that end in 0 or 8 have a non-zero possibility of being primes. So that's the ones you check. And I call this the rubber band test. So look at that graph that I just posted and think about attaching any numbers that have 0 and 8s in those twin prime format, a rubber band in between them. And 2 is the only one that's odd out compared to the other ones I'm going to show you because it's a line. It might not seem like it, but think about at each number that's 0, 8, putting like a little pin and then putting a rubber band on it. The twin primes are the only ones that are going to be vertical, up and down. They're actually lines. They're not areas at all. And that one I just showed you is for the spacing of primes with spacing of 4. As you can see, unlike the twin primes, the spacing of those form rectangles. That is 6 gap on the 5 mod 6 line. That is 6 gap on the 7 mod 6 line. All right, I'm a little over time and everything, but in conclusion, as you can see by those graphs, except for the twin primes, which they're always lines, right? They're always vertical. The rest of the spacings from 4 to infinity in some way incorporate something that looks like a rectangle. It has a hypotenuse, 2 triangles together, which is the crux and problem of finding out the secrets of the primes. So like I said, I'm a little bit over time, but at least this one can get you thinking. And as always, God loves you. Do not hurt each other and try not to lie. I will talk to you later.